Okay, class. So last time I left you with a take-home problem, which is more like a stay home and do the problem now since we are at home. Now, hopefully you did this. So let's go over it together. And if you haven't done it, please pause me, do this, and then we're going to do this together. So last time we started talking about figuring out the pH or pOH of a solution. And remember what I said. I said when you're trying to figure out the pH or the pOH of the solution, what you are looking for hydronium concentration. You are looking for hydroxide concentration. You're looking for H+, you're looking for OH-. That's how you can figure out pH and pOH. Okay. Now in this problem, I don't give you that. I give you ammonia. But what is ammonia? What ammonia is a weak base. Okay? Ammonia is a weak base. So that's where we have to start, that ammonia is a weak base. And I said that when you have weak acid or base, when you have weak acid or you have weak base, don't forget what you have an equilibrium, because they will only partially dissociate in water. So every time you have a weak acid or base, the first thing I want you to do, write down the equilibrium. So in water, I want to have ammonia plus water, and don't forget the basic. Ammonia is my base. If ammonia is my base, that means water is going to act like an acid. So ammonia is my base, that means water is going to act like an acid. The base is going to get a hydrogen, the acid is going to lose a hydrogen. Gets a hydrogen, lose a hydrogen. So then I would end up on this side, I would end up ammonia plus OH-. Okay, so this is my equilibrium. And we said every time you have an equilibrium, we've learned this when we learn about equilibrium, the ice table is back. You're going to do an ice table. Okay, initial, change, and equilibrium. Now, what is the initial concentration? The initial concentration for ammonia is 0.35 molar. And at the beginning, I don't have any of those. What's going to be the change? Since this is the only thing I have at the beginning, this has to go away, and some of this is going to be formed. So minus x, and x. Now at equilibrium, it will be 0.35 minus x, and x. You've seen this before. So weak base, I have a weak base here. Every time I have weak base or acid, I'm going to write the equilibrium. You do the equilibrium, you are going to write down the ice table. And remember, now what we also have an equilibrium constant, which is Kb here, since we have a base. Now the Kb is going to be product over reactant. The Kb is going to be product over reactant. So it would be the concentration of ammonium times concentration of hydroxide over concentration of ammonia. Now, how come I didn't include water? Because we do not include liquid or solid in the equilibrium equation. You guys knew that from previous chapter. Okay, this is going to equal the Kb, and my Kb is 1.76 times 10 to the minus 5. You guys are good so far? Okay. Now, check this out. Here, I don't have those concentration, but this is what I have at equilibrium. So NH4 plus is X, OH is X, and ammonia is 0.35 minus X. So I'm going to plug those in. So it will be X squared over 0.35 minus X. Why is it X squared? X times X, right? So this is my product over my reactant. So far, so good? Okay. Now, to solve this, because this is a small k value, this is much less than 1, what I can do, I can assume that this x is 0. And if I assume this x is 0, that is going to make my math so much easier. And I can assume that because whatever this x is going to be so tiny compared to 0.35 molar, right? This is going to be such a tiny number compared to this, so I can just assume 0 and still get a nice approximate number. So far so good. Okay. Again, I can do this because it's probably such a tiny number compared to this, and my k is much less than 1. So if I do this, if I assume that's 0, then what that's gonna mean, then I'm actually gonna rewrite this to make sure it's on the same page. So I'm gonna write 1.76 times 10 to the minus 5 is an equal x squared over 0.35. Okay, much easier math. And if I solve for x, what I'm gonna get for x is 2.48 times 10 to the minus 3 molar. Now, what does x represent? This is what's really key here. What does x represent? Well, what x is going to represent the hydroxide concentration. That's cool. So this would be my hydroxide concentration. Remember what I said at the beginning. I said, don't forget that what you are looking for. You're looking for hydroxide concentration. You're looking for hydronium concentration. Something H plus, OH minus that can get you to pH and POH. Okay, so I figured out X, and X is my hydroxide concentration. Now this is not bad, right? Now this is not bad at all because you know how to figure out the POH. If I have hydroxide concentration, I can figure out the POH because POH is minus log of hydroxide concentration. Okay, so it would be minus log of 2.48 times 10 to the minus 3 molar. You follow me that? Okay, so my X was my hydroxide concentration. That's great. If I have hydroxide concentration, I can easily figure out POH because POH is minus log of hydroxide concentration. And I'm just going to do that right now. So when I do this, my POH is going to be 2.60. Don't forget, 2 sig fig, and the sig fig counts after the decimal because we have log. So here I have 2 sig fig, and this would be considered 2 sig fig also. Because, one more time, when you take the log of this, the 2 comes from 10 to the minus 3. So this one comes from here. So now if I'm limited to 2 sig fig, the sig fig is going to be after the decimal place. We're good so far? Okay. Now, I have the POH. Okay. I have the POH, but what I need is pH. That's okay. All I have to do, I know the relationship that pH plus POH equals 14. So now all I have to do is subtract 2.60 from 14 and get 11.40, and that would be my pH. So far, so good? Okay, this was a big problem. Remember, if you see a problem like this, when you have a weak acid or base, you go, okay, weak acid or base, what am I going to do? I'm gonna write the equilibrium, right? Weak acid or base, yes, I'm going to write the equilibrium. You write the equilibrium equation here, and then, ice table. We know about ice table. I want to set up the ice table, and then, again, you have an equilibrium constant, product over reactant. When you go through the process and you find X, you go, wait a second, X is my hydroxide concentration. So if I have hydroxide concentration, I can figure out POH. Every time you have OH minus concentration, you can easily figure out POH. From there, after POH, subtract from 14, and you can figure out the pH. So far, so good? Okay. I'm limited to 2 sig fig. For the logs, I have to consider after the decimal place. 2 sig fig, I am good to go. All right, beautiful. Hopefully you got this down. The next thing we're going to talk about is a little fancy, or it sounds really fancy. The next part of this lecture, we're going to talk about conjugates. Conjugates do sound very fancy, but they're not actually fancy. But they sound fancy. Conjugates. Let's go over what is conjugate. I'm not going to define it for you. I'm actually going to give you an example, and then we're going to go over it. HNO2, okay? HNO2 plus water. Here I have an acid plus water. HNO2 is a weak acid. So if you write this equilibrium, again, acid is going to lose a hydrogen. And since this is my acid, water is going to be my base. And the base is going to gain a hydrogen. I know I keep repeating, but it's good to repeat. So acid is going to lose a hydrogen. I'm going to become NO2 minus. And the base, which is the water in this case, is going to gain a hydrogen. Is going to become hydronium. We're good so far? Okay. Now, the conjugate here is NO2 minus. NO2 minus is the conjugate of HNO2. So what is the conjugate? Conjugate is a species that is left over after the acid loses the hydrogen. So after the acid loses the hydrogen, the species, the guy that is left over, that is the conjugate. Not bad, right? So HNO2 is going to lose the hydrogen. When it loses the hydrogen, is left NO2 minus is left behind. That is the conjugate. So conjugate is a species, is a compound that is left after the acid loses the hydrogen. So the acid loses the hydrogen, and this guy that is left over, that's going to be the conjugate. So far, so good? Okay. Again, we're going to do a lot of practice problem with the conjugates, so you will understand it really well. Ammonia plus water. So ammonia is a weak base, right? So we have a base. If this is a base, that means the water is going to be the acid. Okay, write the product for me. The base is going to get a hydrogen. The acid is going to lose a hydrogen. So it's going to be ammonia plus OH minus. Okay. Now in here, ammonium is the conjugate of ammonia. So now what does that mean? So the conjugate, you know how like we said acid loses a hydrogen? Acid loses a hydrogen. So after acid loses a hydrogen, the species left behind is the conjugate of that. Now base gains a hydrogen, right? Base gains a hydrogen. So after base gains a hydrogen, that is going to be your conjugate. Okay, so let's do this one more time. Acid, what? Acid loses hydrogen. So acid loses H plus, base gains H plus. So after acid loses a hydrogen, the species left behind, that's going to be the conjugate. After base gains a hydrogen, that becomes your conjugate. After base gains a hydrogen, that species becomes your conjugate. So far, so good? Okay. Now, what I'm going to do now, I'm going to go over a bunch of weak acid and bases and talk about the conjugate. All right, let's do this. So the first thing I'm going to talk about, hopefully you're following me so far, I'm going to talk about weak acids and conjugates. Again, conjugates, we refer it to the species left after the acid loses the hydrogen, or to the species after the base gains the hydrogen. Now, I'm going to actually draw them out. Because remember Lewis structure from back in the day? Yeah. I'm going to draw Lewis structure because it's cool. So, this guy right here, this one is acetic acid. Acetic acid. And do me a favor, because you guys are fancy now and you know a lot of chemistry. The way we write acetic acid is HAC. That's how chemists usually abbreviate it, because acetic acid, instead of writing it out acetic acid or draw it out, we write HAC. So when you said HAC, you know that's acetic acid. Okay? So, you know, AC basically for acetate, acetic acid. So here's my acetic acid. And in this acetic acid, right here, this is my acidic hydrogen. This is a hydrogen that is going to lose. So, acetic acid is a weak acid, it's an acid. Acid is going to lose a hydrogen. After it loses a hydrogen, what does it look like? It's going to lose a hydrogen. is going to look like this. It's going to lose a hydrogen. When you lose a hydrogen, then all those electrons are going to go to the oxygen. So this is what I have. Now, what do I call this? This is acetate. This is acetate. This is AC minus, right? So when you lose a hydrogen, what is left is this guy, and this is acetate. Now, so I'm hoping you go, oh, hold on a second. In Chem 1A, when we were learning about naming the acid, they said whenever you end with ate, you becomes ic acid. Remember that? This is acetate. When you become an acid, you become acetic acid. This is kind of cool. This kind of goes back in the days when we started talking about acid. So acetic acid loses a hydrogen and then it becomes acetate. Okay. Now acetic acid is a weak acid. Now if you have a weak acid, what does that mean? Weak acid is going to have a equilibrium constant, Ka, right? And the Ka for acetic acid is 1.7 times 10 to the minus 5. Now, I want to quickly go over something that I wanted to go. I forgot. Don't forget, every time you have weak acid or weak base, I need you to remember that you are going to have equilibrium. And every time you have an equilibrium, that means you are going to have a Kb or Ka, right? With acid or base equilibrium, you're going to have an equilibrium constant. All right, so far so good. Now, this is acetic acid. It's going to lose a hydrogen, becomes acetate. So what do we call acetate? What's a fancy name that you learned today about this? What do we call this? This is a conjugate. This is a conjugate of acetic acid. After the acid loses a hydrogen, this would be the conjugate of it. Okay, hopefully you're getting the hang of it. All right, my next acid is called formic acid. This is called formic acid. Okay, formic acid. This is the hydrogen that is going to lose. Okay, so when it loses the hydrogen, what is it going to become? What would be the name of it when it loses hydrogen? When it loses hydrogen, it's going to become formate, right? Formate, formic acid. Okay, so it's going to lose the hydrogen to become formate. Now, I have a weak acid here. Formic acid is a weak acid. So the Ka for this acid is 1.8 times 10 to the minus 4. Okay, what do you call formate? Formate would be the conjugate of formic acid. Formate is after the formic acid loses a hydrogen. I have formate. That would be the conjugate, right? Okay. Good job for hanging in there with me. Next one, HF. How would you name that? You know how to name that one. That is hydrofluoric acid. Okay. After the hydrofluoric acid loses a hydrogen, what's going to be left over? F minus is going to be left over, right? And that is fluoride. And if you remember again, back in Chem 1A, sounds like deja vu. You become a hydroic acid, right? So fluoride, you become a hydrofluoric acid. The good old days, huh? All right, so what is fluoride? What fluoride is going to be the conjugate. This is a conjugate of hydrofluoric acid. So the acid loses a hydrogen, and that species is going to be the conjugate, right? Loses a hydrogen, this is a conjugate. Okay. Now, hydrofluoric acid is a weak acid, which means it has a Ka, and the Ka for that is 3.5 times 10 to the minus 4. All right, ready? I'm going to do one more acid. HClO. Let's see how much you remember your polyatomic ion, so you can name this acid for me. This acid is, hopefully you remember it, is hypochlorous. Is hypochlorous acid. This is hypochlorous hypochlorous acid. So if hypochlorous acid loses a hydrogen, what's going to be left over? ClO minus, right? ClO minus, which is, ClO minus is hypochlorite. Is hypochlorite. So you remember that when you end with ite, you become us acid. So hypochlorite because hypochlorous acid. Ite was us. Ite was hydroic. Ate was ic. So if you remember the naming of the acid. Okay, so again, hypochlorous is going to lose a hydrogen, and a hypochlorite is going to be left over. So what is this hypochlorite? This is, I can hear you guys actually, conjugate. Okay, now hypochlorous acid is a weak acid, so it's going to have a Ka value, which is 2.9 times 10 to the minus 8. 2.9 times 10 to the minus 8. Are we good so far? Okay. Beautiful. Very nice job. Now I have a quick question for you before we move on. These are all weak acid. That's why they have a Ka value. Which one is the weakest of all the weak acid? So I know these are all weak acid, but which one is the weakest of all the weak acid? What do you think? Remember, when I ask you for the weakest or the strongest, you always pick the larger number or the smaller number. Don't pick the middle guy, right? So I'm asking you which one is the weakest weak acid. So I'm either going to go with the one that has the largest Ka or the one that has the lowest Ka. If you remember, we said Ka is product over reactant. And product means H+, right? Because when the acid dissociates, it's going to form H+. So we said the larger the Ka value, you have more H+, you have more hydronium, then it's going to be stronger. So if I'm looking for the weakest weak acid, I would pick the one with the lowest, the smallest Ka. So the smaller the Ka, the weaker acid you are. So out of all these ones, this is my smallest Ka. So hypochlorous is going to be my weakest weak acid. So far so good? Okay. So far you followed that hopefully. We've gone over this. These are the weak acids, the conjugate, and then this is the Ka value for that. Now I want you to pay attention to this conjugate. And something is interesting about this conjugate. All of these conjugate, they have a minus charge, don't they? Minus charge means they have extra electron. Minus charge means they have extra electron. If they have extra electron, what does that mean? Remember, go back to day one. We said that acid is going to lose a hydrogen, base is going to get a hydrogen. And we said that base can get a hydrogen because base has extra electron to afford that hydrogen. Because remember that? We said base has extra electron so it can afford that hydrogen. Because if you want to grab a hydrogen, you better have the extra electron to be able to do that. Now, can you tell me about all these conjugate? All these conjugate have extra electrons, don't they? Now they can act like a base. Now they can act like a base, can they? They can. Now they can act like a base. Okay, so now they can act like a base. So now what does that mean? So what that means is when you have an acid, when you have a weak acid, the conjugate is going to be basic. So the conjugate is going to be a conjugate base because now it has extra electron and it can act like a base. It can act like a base. I'm going to repeat it one more time. So you got what conjugate is. When you look at all this conjugate, they have extra electron. And we said when you have an extra electron, you act like a base because now you have the extra electron to go and grab the hydrogen, right? So these are all conjugate base. Are we good so far? Okay. So when you have a weak acid, the conjugate is going to be basic. All right, now next one, let's go over a couple of weak base and its conjugate, okay? Weak bases and conjugates. Now, the same thing as before, don't forget, that hasn't changed. That weak acid or base, they have equilibrium. If you have an equilibrium, you have an equilibrium constant. Don't forget that. All right, our favorite base, ammonia. I'm actually going to draw out ammonia. This is a Lewis structure of ammonia. You probably remember that. Okay, so again, you look at ammonia. What does it have? This is a base. It has lone pair, right? It has this lone pair. It has extra electron to be able to grab a hydrogen. So ammonia is a base, is going to get a hydrogen, right? Is going to get a hydrogen. When it gets the hydrogen, now is going to be electron deficient, right? Because it uses this electron to grab a hydrogen. Now we call this what? We call this ammonium, right? We call this ammonium. And remember that ammonia is a weak base. So it's going to have a Kb, which is 1.76 times 10 to the minus 5. So far, so good. So ammonium is going to get a hydrogen. Once it gets a hydrogen, it forms ammonium. What do we call this? This is a conjugate, right? Again, acid loses a hydrogen. That guy is conjugate. Base gains a hydrogen. This guy is the conjugate. So far, so good. Okay, let's do one more base. This is a base you probably haven't seen before. Here's my base. What we call this one is dimethylamine. Dimethylamine is a base because it has a lone pair, right? It's going to grab a hydrogen. If it grabs a hydrogen, so it's going to be a hydrogen here, and the rest remains the same. Is grabbing a hydrogen, okay? And again, dimethylamine is a weak base, so I'm going to have a Kb for this. The Kb is 5.9 times 10 to the minus 4. Okay, now it gains the hydrogen. Now what do we call this guy? We call this guy the conjugate. We call this guy the conjugate. So far, so good? Okay, now pay attention to this. This is what's very interesting. So look at these conjugates. These conjugates, this is the conjugates of the weak bases. They don't don't forget this is a plus charge because now it's electron deficient because it lost it donated the lone pair to grab a hydrogen. Now I have an extra hydrogen and it has a plus charge. So when you look at these two, these are the conjugate of the weak acids. Now they don't have minus charge anymore. They don't have lone pair anymore. They don't have extra electron anymore. What does that mean? So if they don't have any extra electron anymore, can they act like a base? They can't. But now what they have, now they have extra hydrogens, don't they? So they are electron deficient now, and now they have extra hydrogen. So now what they are going to do, they are going to act like an acid. So they're going to act like an acid. That's kind of cool, right? So now they are going to act like an acid. Okay, so what did we learn? This is what we learned. If you have a weak acid is going to have a conjugate that is going to act like a base. Is going to have a conjugate base. Now, if you have a weak base, what's going to happen? You're going to have a conjugate that is going to act like an acid. You saw it. This conjugate now doesn't have any more extra electron to act like a base. Now it has an extra hydrogen. It's electron deficient. It could act like a base. Okay? It could act like a base. Are we good so far? Okay. Very nice job for hanging in there. Now, the next thing we're going to talk about, we are going to talk about this situation. Here's an interesting situation. I have pure H2O And if I measure the pH of that, it's 7. If I have pure NaCl salt, if I measure the pH of that, is pH of 7. Now, I'm going to have sodium acetate. You know, AC means acetate. That's also a salt. The pH of that solution is basic, is larger than 7. And if I have an ammonium chloride salt dissolved in water, the pH of that is going to be 7. Okay? So here's our scenario. If I have pure water, the pH is 7. You know that. If I have pure NaCl dissolved in water, right, the pH is also 7, right? Now remember, NaCl is what? NaCl is a salt, right? NaCl is a salt. So I'm going to have this salt dissolved in water and the pH is going to be 7. Sodium acetate and ammonium chloride are also these salts and they are also going to be dissolved in water. But these two, their pH are not 7. I have a basic and I have a acidic pH for those. Now the question is, what's going on? I'm going to repeat the scenario one more time. If you have pure water, you know the pH is 7, right? We measure that, pH is 7. I'm going to add NaCl, which is salt, to water, and I'm going to measure the pH. It's going to be 7. Then I'm going to add sodium acetate, which is a salt, to water, and the pH is going to be more than 7. It's going to be basic. And then I'm going to take ammonium chloride, which is a salt, add it to water, and the pH is going to be less than 7. So what's going on? I added NaCl salt to water, then water has a pure pH of 7, pH was 7. I added sodium acetate, the pH became basic. I added ammonium chloride, the pH becomes acidic. What is going on? What is going on here? Here is what's going on. I'm going to show you. And it has to do with conjugate. Conjugate acid and base. Conjugate acid and base can hydrolyze to form the weak acid and base. And you're going to look at it and it's like, what is she talking about? This is why I don't like to define things, but I'm going to show you. I just want you to be on the same page as me. So if I have just pure water, the pH is 7. I add NaCl salt, pH stays 7. I add sodium acetate salt. Whoa, what just happened? Now why is my pH basic? I add ammonium chloride salt to water. What? The pH became acidic. What is going on over here? What's going on has to do with the conjugates, okay? What's going on has to do with the conjugates, all right? So now let's do this conjugates to see what is going on. So what's going on? We call it hydrolysis. The conjugate acid and base can hydrolyze to form weak acid or base. Now, let's say F minus. I want to make sure you understand this. F minus. F minus is a conjugate of what? Think about this. So F minus is a conjugate of HF, right? So F minus is a conjugate base of hydrofluoric acid. You guys agree? Okay. So hydrofluoric acid, weak acid, when it loses a hydrogen, F minus is left over. So F minus is a conjugate base of HF. And we said when you have a weak acid, the conjugate is conjugate base. It's going to act like a base because now it has a minus charge. It has an extra electron. So far, so good? Okay. Now, I'm going to write, again, we said they can hydrolyze in water. So what that means is I'm going to have F minus plus H2O. I'm going to have hydrolysis. Now, remember, we said that F minus now is a conjugate base. Do you agree? So it's going to act like a base. So F minus is my conjugate base of HF. It's going to act like a base. It has a minus charge. It has extra electron. It's going to act like a base. So if F minus is going to act like a base, which means water is my acid. Okay? Now what's going to happen? The base is going to get a hydrogen. The acid is going to lose a hydrogen. The same as before. The base is going to get a hydrogen and the acid is going to lose a hydrogen. You guys are good so far? Nothing. Nah. I didn't do anything funky. Okay, so F minus is a conjugate base of HF. It's a conjugate base. We talked about this. It has a minus charge, extra electron. It can act like a base. This is my base, which means the water is going to be my acid. The base is going to get a hydrogen. The water is going to lose a hydrogen. This is what I get. Now, isn't it interesting? I end up having OH minus in the solution. So I end up having an OH minus in the solution. So what that means is I'm going to end up having a basic pH, don't I? Okay, I'm going to end up having a basic pH when I have that conjugate base in my solution. Yeah, let's do another example. NH4 plus. NH4 plus is the conjugate of what? Is a conjugate acid of ammonia, right? So ammonia is a base. When it gains a hydrogen, it becomes ammonium. And we said that when you have a weak base, the conjugate is going to be acidic, right? The conjugate is going to be acidic. It has an extra electron, is electron efficient. Now it acts like an acid. So I want to do hydrolysis. Ammonium plus water, okay? Ammonium plus water. Now, we said this one is going to act like an acid, right? So if the ammonium is going to act like an acid, which means water is going to act like a base. So ammonium is going to act like an acid, which means water is going to act like a base. So the acid is going to lose a hydrogen. The base is going to get the hydrogen. So the ammonium is going to lose a hydrogen, becomes NH3, and water is going to get a hydrogen because it's a base now, becomes hydronium. Don't forget, charges on both sides has to be the same. -1 overall, -1 overall. +1 overall, +1 overall. Okay? Now, whoa, look at that. I have hydronium. I'm going to have an acidic pH, aren't I? I have a hydronium. So I'm going to have an acidic pH. So what's going on? What was going on over here? I was having some conjugate. When you have conjugate can hydrolyze to form weak acid and bases. As you can see here, if I have F minus in the solution, it could add plus water, it can do the hydrolysis, and I end up having a basic solution, right? I end up having OH minus. If I have ammonium, which is a conjugate, it's going to hydrolysis, add into water, I'm going to end up having hydronium. So I can have an acidic pH. Yeah? Okay. Does this make sense? I don't like definition. If this makes sense, I like that. I like that a lot more. Sounds good? Now, last thing I want to mention. So when you have an F minus, since you have an OH minus is produced in the solution, now what I'm going to use, I need a KB. Now over here, what I need a Ka. Because remember, the conjugates, when we call them conjugates, conjugate base is going to act like a base. This is a conjugate acid, is going to act like an acid. That was really hard for me to kind of grasp when I was undergrad. I want to make sure you guys are understanding it, that yes, this is a conjugate, but it's a conjugate base. What that means is it will act like a base. It is acting like a base, so I need a KB. This is a conjugate, but it's a conjugate acid, so it's going to act like an acid, so I need a Ka. So far, so good? Okay, I'm going to stop here. It's a lot of concept went over. Hopefully you follow that. And next time, we're going to do practice problem, and we're going to kind of make sure that you understand the concept as we're doing the practice problem. Nice job hanging in there with me. Make sure you go over the concept, get the concept down for me, and we'll do plenty of practice problem next time. I will see you next time.